When you flip the switch, does electrical energy flow through the copper inside the wire? Surprisingly, most electrical energy does not travel inside the wire. It travels through the space surrounding it. We tend to think of wire as a pipe that water flows through. But in reality, energy moves along the electromagnetic field formed around the wire, what physicists call the Poynting vector. The wire isn't a pipe that contains energy. It's more like a guide rail that directs where the energy goes. This is also why copper wires stay cool while a filament glows. Energy only bends inward and gets absorbed where it meets a resistance. Copper has so little resistance that energy barely seeps in and mostly skims the surface. The filament with much higher resistance pulls energy inward where it collides with atoms and turns into heat and light. The bulb lights up instantly when I flip the switch. Doesn't that mean electrons are running at the speed of light? No. The average drift velocity of free electrons inside the wire is typically only a few millimeters per second. Yet, the bulb lights up almost immediately because the moment you flip the switch, the electromagnetic field propagates through the entire circuit at nearly the speed of light. This electric field reaches the free electrons already present in the bulb filament almost simultaneously, causing them to start moving right away. In other words, what moves fast is not the electrons but the change in the electric field. The electrons begin moving slightly, simultaneously at various points throughout the circuit. Does a battery die because it runs out of electrons inside it? No, a battery doesn't create or store up electrons to dispense. The circuit itself already contains all the free electrons it needs. What the battery actually does is use chemical energy to separate charges and create a voltage. That voltage sets up an electric field through the whole circuit, which pushes the existing electrons into a slow drift. That's the current. So, when a battery dies, it's not that the electrons run out. It's that the chemical energy needed to keep that voltage and the field it creates has been used up. Isn't flipping a switch just connecting two pieces of copper wire? No. Physically, something far more important happens. The moment the switch closes, an electric field forms throughout the entire circuit almost instantly, not just at the point where the metal touches. This new field triggers the flow of electromagnetic energy along the space around the wire all the way to the lamp. That's why the switch isn't simply a door connecting two wires. It's the trigger that sets up the field and energy flow across the whole circuit at once. Isn't lower resistance always better? No. It's thanks to resistance that we obtain light and heat. Electromagnetic energy traveling through space is converted into heat through collisions between free electrons and the atomic lattice in materials with resistance. In a light bulb filament or electric heater, this process is maximized, producing light and heat. Additionally, resistance acts as a safety device that limits excessive current. While low resistance is desirable for power transmission and signal delivery, resistance is an essential component for applications involving heat generation, lighting, and current control. The switch and bulb are actually only 1 meter apart, but suppose the circuit is built from two parallel wires, each 300,000 kilometers long, running out and back to connect them, 600,000 kilometers of wire in total. Wouldn't the signal need at least 2 seconds to travel that full distance before the bulb could light up? Not at all. The bulb begins to light up in about 3.3 nanoseconds. This is the famous lamp switch paradox. We naturally assume energy must travel down every kilometer of wire like a train on a track. But as we've seen, electrical energy actually travels through the space around the wire guided by electromagnetic field. So what matters isn't the wire's length, it's the direct spatial distance between the switch and the bulb. The moment the switch flips, an electromagnetic field erupts into that 1 meter gap and crosses it at nearly the speed of light, about 3.3 nanoseconds. When it reaches the filament, free electrons there begin to drift almost instantly, and the bulb starts to glow faintly. The energy doesn't wait to complete a 300,000 kilometer round trip to reach the bulb sitting 1 meter away. Full, stable, maximum brightness takes about 2 seconds, the time for the whole 300,000 kilometer wave to travel out and settle, but the initial reaction happens in a fraction of a microsecond. Thanks for watching. If you found this video helpful, give it a thumbs up and don't forget to subscribe to the channel.